The problem statement from GATE Physics 2014 reads as follows. The value of the integral z square over e to the power z plus 1 dz over the contour C, where C is the circle mod z equal to 4 is. This is a multiple choice question with one correct answer, and we're required to find the correct one. But first, let's have a quick look at the Cauchy's residue theorem, which can be used to evaluate the integrals of the kind that we see in the question. So the theorem states that if we are given an analytic function fz, so this function is analytic inside this contour C, except at finite number of points, so we call those points singularities. So this fz is analytic at all the points except for these n purple points, which we call the singularities. Then the integral of this function fz over this closed contour C can be given by 2 pi I and sum of all the residues evaluated at the singularity points. So, but now the next question then arises, how do we evaluate the residues at these singularities? So we can evaluate the residues using two approaches. First one is the limit approach, which is beneficial when we have simple poles. And second thing, the second approach is the series expansion, which we use typically for exponential functions or trigonometric functions. Right, so we are required to evaluate this integral, and we have seen that we can evaluate this integral, such form of integrals, using Cauchy residue theorem. So in this case, our fz is z square over e to the power z plus 1. Now you can see the numerator is analytic, z square is analytic everywhere. Similarly, the denominator e to the power z plus 1 is analytic. However, so we'll see, at first look, it looks like this function is analytic, but you can see a problem. When denominator goes to 0, singularities will arise. So again, so we can see that some singularities will arise except at some finite amount of singularities. So we'll see whether they're finite or not. Okay, so except at some singularities which we denote by zk. And how do we evaluate the singularities? We'll simply say when the denominator goes to 0. So I'll take minus 1 to the right side. So what I can say that this e to the power z, so you can say that this is, I can write as e to the power I theta, where theta is, let's say, pi. So if it's I'll just tell you what I have, 5 pi, and even negative ones like minus pi, minus 3 pi, and so on. So let's try to do for e to the power I pi. So e to the power I pi can be written as cos pi plus iota sin pi. Sin pi will go to 0 and cos pi is minus 1. So you can see that e to the power I pi will be minus 1. However, if it were even powers, 2 pi, then it will become plus 1, but we want minus 1. So that's why only odd powers of only odd coefficients of pi should be taken, right? So so alternately I can say that e to the power z equal to e to the power I 2k plus 1 pi, where k is an integer. You can see that if k is an integer, so you can say k equal to 0, it will become pi, k equal to 1 will become 3 pi, and so on. So by simple comparison, I can say that zk is iota 2k plus 1 times pi, where k is an integer. So we have seen that. So these are the singularities that we have evaluated, right? So let's try to plot them on our curve. So when k equal to 0, it will be iota pi, right? So iota pi is approximately 3.14, right? So it will be somewhere over here, right? So I'm writing it as I pi. Similarly, when let's say k equal to 1, it will be valued to be 3 pi. So 3 pi, iota 3 pi, sorry. So iota 3 pi will be like 9.4 something. So it will be over here. So I'm writing it as here. Let's extend this. So it will be iota 3 pi. It's falling outside, you can note that. Similarly, when k equal to minus 1, so this will come out to be minus iota pi, and similarly other values would be minus iota 3 pi on this negative y-axis over here. So you can see that only two singularities are falling inside the contour, and they are finite. We notice that there should be finite number of singularities inside the contour. So now we can simply say that so we found out the singularities. So we found out the singularities which were I pi and minus I pi, and we can know that this is equal to 2 pi I residue, sorry, sigma k equal to 1 to 2 residue of fz at z equal to zk, right? So I can simply expand it 2 pi I, so there are two residues, so residue of fz at z equal to I pi plus residue of fz at z equal to minus I pi. There are only two singularities inside the contour, so we are doing that. So now let's just evaluate the first residue. So first residue is residue fz at z equal to I pi. So we'll use limit approach because this is a simple pole, so we can use a limit approach. So we'll say limit z goes to I pi z minus I pi multiplied by the function fz. This will come out to be limit z goes to I pi z minus I pi, fz is z square over e to the power z plus 1. Now this is a 0 by 0 form. If you put z equal to I pi, this is 0. This will also evaluate to 0 because you just notice this is a simple pole, right? So if we apply the L'Hopital rule, so what we do, we independently differentiate the numerator first. So limit z goes to I pi. So if you differentiate the numerator, it's z cube, so it will become 3z square minus 2z I pi, and then we differentiate the numerator, it will come e to the power z will remain the same and 1 will become 0, right? So now if you put the limits, it's no more a 0 by 0 form. So let's do that. So 3 I pi square minus 2 I pi times I pi over e to the power I pi. So this will becoming 3 I pi square minus 2 I pi squares. This will become iota pi square over, we saw that e to the power I pi is minus 1. So this will come out to be iota square pi square over minus 1. Iota square is minus 1, so this will come out to be pi square. So we have evaluated the residue at z equal to I pi is pi square. Similarly, if we evaluate residue of this function at z equal to minus I pi using the same approach, the limit approach, and this time we'll multiply by z plus I pi fz. So this will come out to limit z goes to minus I pi z plus I pi z square over e to the power z plus 1. Again, this is a 0 by 0 form, so again I'll apply the L'Hopital rule. So this goes to minus I pi. If you differentiate it, again this will become 3z square plus 2z I pi divided by e to the power z. If you put again the limits, it will come out to be, so 3 minus iota pi whole square, 3 minus iota pi whole square, plus 2 minus iota pi and then iota pi, okay? So over e to the power minus iota pi. So yeah, that's that. So if we try to evaluate that, so this will come out to be, there's a negative sign here, so this will come out to be this will be plus and this will be minus, so we will get minus pi square in the numerator over e to the power iota pi is minus 1, so again we'll get pi square. So both the residues are coming out to be pi square. So I'll write that on the next slide. So we saw that, so this I was coming out to be 2 pi I and the sum of the residues. So first residue was pi square, the second residue was also pi square, so this will come out to be 2 pi I into 2 pi square, which will come out to be 4 pi cube iota, which is our option C. So that will be the correct answer. Key thing to note in that was that we only took the singularities which are falling inside the contour and evaluated the residues there. Thank you for listening.